Carol Stoker, welcome to Mars Talk. Now, you were a co-investigator for the Phoenix Mars mission, a mission that made a number of important discoveries, but I think none more interesting, or at least more sort of titillating, than the discovery of perchlorate in the soil at that site. Talk about why that is such an interesting discovery.
That was a fundamental change in our thinking about the way the surface of Mars behaves and could behave, because perchlorate is a salt, and it is a eutectic solution of perchlorate is liquid at current Mars temperatures, at current Mars polar temperatures. So it, right away allowed people to. There was a glaciologist on our team who immediately wrote a paper about the movement of glaciers on Mars, which has always been a puzzle. As how could you have the polar caps appear to be like flowing, moving glaciers, and they should be stuck because of the temperatures that they're at. And this allowed you to actually have like glacier flow, glacial surge at Mars temperatures by, well, you just got this salty layer that the glaciers are sitting on. There had always been speculation about salts on Mars and the presence of brines and the use of, or the fact that briny water could be liquid. But this is a very unusual kind of salt. This is not at all common on Earth. Well, in fact, it was common in one place, and that was the Atacama Desert in the big nitrate deposits, which now have all been mined out. But they had concentrations of perchlorate at comparable amounts to the amount on Mars. Now, this discovery has very profound implications for life and very profound implications for human exploration. And it has, it's certainly been talked about, but it kind of hasn't had the sea change in people's thinking that I think it needs to have and should have had.
Does this discovery help better explain some seeming evidence for liquid water in other sites at Mars, for example, inside of crater walls or on hillsides where water seems to be seeping?
There's about 0.5% perchlorate in the soil at the Phoenix site. We don't know if that's a local phenomenon or a global phenomenon. If it's a global phenomenon, then yes, because the thing about perchlorate is it's incredibly hygroscopic. So it attracts water to it. It pulls it out of the air. I mean, if you have a tube of powdered perchlorate sitting on, if there was one sitting on this table with the cap off, in a few hours it would be liquid. It would just be swimming in water because it just pulls water out of the air. It also is used like oxygen by organisms. So it's an oxidant. It's a strong oxidant, and microbes use it with basically any kind of reductant for an energy exchange mechanism. And it's lots of organisms can do it. It's a quite common chemical energy source for life on Earth. So what that means, if you're a microbe on Mars, is you can live underground. You don't have to live at the surface, where it's actually a pretty bad place to live for a couple of reasons. There's basically sterilizing ultraviolet radiation. So in fact, Andy Sugar, who's a biologist who's studied this, has shown that in something like an hour on the surface of Mars, just the sunlight sterilizes the surface, and there's nobody, radiodurans or anybody else that can actually get through that. So you have to be under a couple of millimeters at least of soil to be a viable organism. What happens is,
at that point you're giving up on photosynthesis.
Well, that's the problem. It's really, there are probably niches, the under the transparent rock, kind of niche that things could still do photosynthesis, but it's likely that you're going to want to live underground. I mean, the more comfortable place is underground, but then you got to have a chemical energy source. So perchlorate gives you that. But the other thing it gives you is thin films of liquid, because if there's perchlorate there and there's almost any humidity at all or any source of ice, it's going to melt it. If the perchlorate at the individual grain level is sitting on ice, it's going to melt a little hole around itself. Because basically at the thin film level, it'll be at the eutectic point. And, this is why in the Canadian Arctic, where it's, 40 or 50 below zero, you throw salt on the roads and it melts the ice on the roads, even though it's way below freezing, because the salt itself is going to create a eutectic solution of salt and water that's going to have the freezing point of that eutectic solution, which is usually, many tens of degrees below the normal freezing point. So the eutectic solution of perchlorate is like minus 70 almost, 68 or 70. So it's really going to make liquid environments. Now, are those liquid environments at the eutectic point, are those habitable? Typically not, right? So you need to dilute it a little bit. In other words, you need the water to not be at the eutectic. But the other thing that happens is you've got near surface ice at that site, and it's only like a few centimeters under the surface, just like 2-3 inches under the surface. And right now, it's very cold in the summer because the sun is farthest away from Mars during the summer. But the tilt of Mars changes over time, and basically you have periods where where Mars is tilted towards the sun when it's closest to the sun at the North Pole. And that happens only on a 50,000 year cycle. So, that means that every 25,000 years, it's actually warm enough in the North Polar region to melt the ground ice, or to melt anything that's sitting at the surface, several tens of days a year, right now. Right now or 25,000 years ago, right? And it's periodic. It repeats. So what you have in that niche is you have a place where periodically it's warm enough, there's liquid water, there's something to eat, it could support life. I mean, if you were to put, a handful of Antarctic dirt on Mars at that site, and come back in 100,000 years, you would definitely see that stuff had grown and colonized the area.
It's that clear, you feel?
Yeah. I think it's a slam dunk. Now, that doesn't mean that there is life there now, because that actually requires that life ever developed on Mars, and it's made it through all of Mars history and evolution, and is still there today. But if it isn't, then that actually means that life either never developed on Mars or was extincted at some point. So it is a habitable environment, and if there's life on Mars that made it through, Mars history, that's where you should find it. You shouldn't have to go, kilometers under the surface to get to a deep, hot biosphere.
Okay, so with this in mind, and knowing that over the years, Earth and Mars have shared a lot of material, and from the Earth to Mars direction, a lot of material with no doubt a lot of healthy microbes inside. Can you even imagine a dead Mars at this point?
The transport of material between Earth and Mars, it would be very surprising if life were not part of that transport of material back and forth. But I think that that climate cycling on Mars is drastic compared to how it is on Earth, and that it is a very significant stressor for life on Mars. And it's clear that Mars is not a Gaian planet in the sense that Earth is. Otherwise it would be unambiguous. If you were on Mars looking at Earth, it would be unambiguous that there was life on Earth. Yeah. It's ambiguous at best if there's ever been life on Mars, and I think that if there isn't, it's really because the environment has been through cycles that are just simply not that life can't get through those cycles, and that's even true in the polar regions. What I'm describing is a habitable environment that is basically a modern habitable environment. But what you have is the orbital parameters that characterize Mars, and in particular characterize the North Polar environment, change over time. And they go through periods when the tilt and, orbital parameters are optimized for essentially warm conditions. They're very habitable. They're much more habitable than they are today. But then there are other periods that are the opposite. And during those periods, it can be millions of years where there's no opportunity to metabolize. So then the problem is, can that life get through those long periods, without becoming basically unable to revive?
I wouldn't see why not in a spore kind of an dormant sense.
Well, the reason why not is actually that there are mechanisms that's destroying the DNA or destroying there's basically galactic cosmic rays that are cooking the material, and the evidence is that you have to bury the material over deeper than about a meter or a couple of meters in order for it to be able to last and remain viable over a period of time that is longer than a few thousand years.
Oh, really? Okay.
So really, what has to happen is if this environment is habitable, it's habitable only at the surface and only for short periods of time each year, right? So then what has to happen is somehow that life has got to get below the surface, quite a ways below the surface, a couple of meters below the surface, in order to be shielded from being destroyed by cosmic rays during the long periods of time when the surface isn't habitable. And then it has to get back to the surface when things warm up again. So that is all a complicated, set of processes. And, yes, you can imagine scenarios where it might happen, but it's not by any means, guaranteed that it's happening.
What are some of the other places we would go to search for life? We think maybe Titan, although that would be a very different kind of life. Enceladus, also at Saturn now. For sure, Europa, I think. Where else will we continue the search for life?
So, yeah, that's one that I don't follow the logic. The Europa for sure.
Okay, good.
Maybe I'm just a contrarian, But, the fact that people wrote science fiction novels where, Europa was this big living planet does not convince me in any way that that's a good place to look. For one thing...
Well, it's kind of the poster child for the follow the water thing. It's like, okay, yeah, here's the water. Oh, plentiful. But you're saying that it's not enough.
Well, yes, there's water, but there really isn't energy, I mean, the problem is the energy and the water are really very far apart. Kilometers of ice apart. And if there is a habitable environment, it's so far below the surface that it's going to be extremely, I think, impossible. I think it's not going to happen in my lifetime or, your child's lifetime that we'll have the technology to get to it. That's the problem. So if you need an environment that's more accessible.
Where is that, Carol?
Yeah, so I think Enceladus is probably the best bet at this point from the new news I'm hearing. Primarily because it's spouting the water out at you. You just need to go collect it. You don't need to drill hundreds of kilometers of ice. We have a very strong case for a habitable zone at the Phoenix landing site on Mars, and strong enough that we should go with a life detection mission and determine if there's life at that site. But that idea doesn't seem to really get any traction, in terms of mission planning. I think that we have followed the water long enough, frankly, because, if you look at the kind of the history here, you had this sort of Lowellian view of Mars that preceded the Viking mission. And frankly, there was a rush to go to Mars with, the very latest in life detection technology of the 1970 era, and land on Mars and search for life. And then there was also a rush to judgment about what the data meant. The Viking mission sort of killed the Mars program for a long time. The results of the Viking mission. And moreover, I don't think it was the results of the mission as much as it was the interpretation of the results of the mission. Because for 20 years after Viking flew, there was no other Mars mission. And the next mission that flew after Viking actually failed. It failed to achieve Mars orbit. And that actually set off, strangely enough, I mean, you know, that could have possibly caused the death of the mission, but it actually set off the modern program where there's a mission, has been a large set of missions, kind of one following on the heels of the other. They took the payload and they split it into 4 missions. So each of these missions got to fly one of those instruments, or, you know, a subset of the instruments that had been on that original mission. So the original mission was a very expensive mission. And the program strategy became fly cheaper missions with less payload, but we have these instruments we've already built. So we basically build copies of these instruments and fly them on individual orbiters, plus other instruments got added. So that is actually what got us into this cadence, you know, of like a mission every opportunity. I believe that that's ending now because, again, the mission costs, the individual mission costs have gone up, have skyrocketed to the point where it's just not feasible to have, you know, a MSL class mission every 2 years. The whole idea of this, you know, it was the cheaper, faster, better era that was ushered in by Dan Golden. That was, you know, fly a cheaper spacecraft with less capability, but fly them more often. And I think that has been a really, really good strategy. And I'm loath to see the program turn away from that because, again, you know, if you have a mission failure and you have a billion-dollar or multi-billion-dollar class mission, it's devastating because people have waited 10 years for that, you know, that data. And if that mission fails, it's totally devastating to the community. Whereas these smaller missions, if one of them fails, well, okay, you wait for the, you know, the next opportunity. And plus, always having new data, you know, always having a new kind of data or new opportunity to build your instrument and get it flown has been very energizing to the scientific community.
Do you have any concerns about Mars Science Laboratory being too much in the old mode in terms of putting all of our eggs in that one basket?
Well, there's no question that the Mars Science Laboratory is a flagship class mission, and that is the flagship class mission mode. And yeah, I think it is not the healthiest way for the community to proceed because it, you know, if that mission fails, it's going to be a disaster. And also, you know, it's just a fact of life in the amount of money that's available to do planetary exploration and the fraction of that money that's available to focus on Mars. You just cannot have spend that much money on a mission and have more than like one a decade. That's just how it's going to be. So, you know, to me, it's actually, you know, the Mars exploration rovers were very productive. I mean, look how productive they were. And they end up being like, for 2 of them, 1/3 the cost of the MSL. So, and even at the time, that seemed, you know, exorbitantly expensive compared to, say, Phoenix, you know. So the fact of the matter is we need to get the cost of doing individual missions down. And one of the ways to do that is to do them, you know, in the kind of more scout or discovery mode where they're PI driven, they're focused objectives, and they are they happen often. They're in a high cadence.
Okay, so that's it. We've been in this mode of, you know, better, faster, cheaper, faster in the development, but I think people had often also thought faster in the actual mission. And what's happening with some of these missions, for a global surveyor, for example, and Spirit and Opportunity, is that they go on forever. At some point, do these missions just need to die, or is it good that they very much exceed their 90-day, guarantee from the car dealership?
The main discoveries from Spirit, the one that they've just turned off,
Yes.
that rover actually didn't have very much exciting, interesting scientific results for the first year, because where it landed wasn't all that interesting, and or it was, its interest ran out pretty quickly, and that is primarily because they landed in what they thought was, morphologically looked like a lake deposit, but chemically didn't. Right? So once they get on the ground, what you can really explore is the chemistry, because, that's sort of the ground level interaction. And it was just a big basalt flow. So they had to crawl off of that basalt flow, and it took a long time to do that because they're not fast. Robots do not go fast. And so after a year, roughly, they got into an area where it was really interesting. And I think had Spirit kept going, they would have continued to have had major results. The discovery of massive silica deposits and things like that, home plate, they're, salts, and it's really major discoveries happened very late in the mission. So, I think that from the point of view of their scientific contribution, the longer they ran, the better off it was. I think it was exhausting for the teams to actually operate them every day, because it's very, very labor intensive to get an uplink to a rover every single day, or to any kind of spacecraft, to make it do new things every day. It's very, very challenging to both the science and engineering team to keep that going. But what it allowed actually was for new people to get involved. The original team burned out. Okay, fine. Put in new people who aren't burned out, and keep going. And broaden the community interaction. I mean, I don't think it ever happened, but I think it could happen and should happen, where grade school kids drive the rover, because it's something that allows community engagement in a way that I think other things don't. I mean, now, and we had this problem on Phoenix, that people think of planetary spacecraft as things that drive, They don't even think of things that don't drive, stationary landers, as even possible anymore. I can't tell you how many times people asked me about Phoenix, where is the rover now? Well, Phoenix was not a rover. What Phoenix did not require moving. But that was a hard concept for the public to get, because it's just become kind of like Kleenex, is something you blow your nose in. I mean, you put something on the surface of a planet and it's going to drive. And that is how people think of it. But it's actually not. It's more expensive to do that, and it's more complicated to do that than to put down a stationary lander.
With all the robots and orbiters in the past, well over a decade now, continuously building up gig after gig after gig of data, and data that some of which will never, maybe never be seen by a human eye, because it just keeps building up. It's sort of like the general problem with science on Earth. Now we have the same problem on Mars. Do you ever think that you and your colleagues would just look at each other one day and say, okay, that's it. We can relax for a little bit. We've got enough data, and we'll just use let us go through this before we build any more spaceships?
That's an interesting question. It is a fact that having 20 years between the Viking mission and the next mission allowed, or actually forced, a very, very large amount of data mining to occur. So that data got really worked over. There was virtually no Viking orbital imaging data that didn't have at least one set of eyes looking at it. There's definitely a lot of data now. And is there as many people looking at the data, per unit bit as Viking? Certainly not. I think, frankly, the limitation on the data mining is money. it's kind of a fact of life that there's a much larger investment in getting the data than in actually looking at it. The NASA Enterprise is very, very focused on building stuff and flying it, and not so focused on funding the scientific community to do the data analysis. And there certainly, which is not to say there's no money in that direction, but that is the throttle on how much of the data gets used. And I think there's unfortunate examples where there's always more money for building the hardware and getting it to the surface of the planet than there is for operations. And so, not so much on Spirit, because they really did keep Spirit going as long as it could, but on Phoenix, they cut the operations budget while the mission was still functional and getting data, and would only get data for a short period of time anyway, and that actually hastened how quickly the mission died. So, there are judgments made about where are we going to spend our resources that could be optimized differently, I think, to get more product out of the data. But the truth is that data is not going away. I mean, it's stored forever. And that's actually one thing that's changed over time. If you go back to Apollo, I mean, one of the things that's happened in the last couple of years has been to try to restore and, archive and rescue the Apollo data, because it wasn't, in many cases, it wasn't, those data records weren't in an archival format. They weren't on the internet. They were stored in somebody's closet in their lab, and
Area 51.
Right. It's almost like Area 51. There's I'm sure that's true of many of the older planetary missions as well, like the Voyager missions. Who's got a 16-track tape recorder reader anymore, I mean, I remember these huge data tapes that my Voyager data was on, and I don't know what's happened to that data. I don't know if that it's really ever been properly, made available to future researchers.
Let me ask you, how does it change your mission when the data you're gathering for something you've focused on for years is made available so quickly to everyone else in the world who's interested in getting it? How does that change the mission?
On Phoenix, what we experienced was that the most amazingly beautiful and incredible data products were basically presented to us by, non-team members who posted them on the web, right? I mean, people who were experts in image processing, or artists, or, graphic artists or whatever, who would make the beautiful color panorama before we would have time to do it. We the science team operating the mission.
That must have been incredibly satisfying. I mean, and fun.
No, it was terrifying. I mean, we definitely had experiences where we had to have a press conference to explain something that was already out in the blogosphere because people had seen it on the images that were being streamed onto the web.
Okay. So yeah, actually horrific.
No, but I mean, it's like you expect as a team member on one of these missions that you're going to make the first publication or statement about the data, right? That's actually kind of why you're doing it. And then the data's out there on the web, and the whole universe has access to it. And, guess what? There's 7 billion people in the world. Some of them might have spotted something you missed. I had the expectation of a young person, that this was going to happen, not just in my lifetime, but in my chance to get selected and go kind of lifetime, right? I mean, it was inconceivable to me that 30 years later I would be, hoping against hope that I would be selected to be on a robotic mission, I mean, I was going to have already been there, done that, right? I mean, it was just a fact of life that we would have humans on Mars in the probably in the 90s is what I was expecting at that time. If you go back to when Wernher von Braun proposed it to Richard Nixon, you know, the program would have had humans on Mars in 1984. That was his landing date. And that was at the end of Apollo, right? Had Apollo continued at the pace that it was going in the 1960s, we would have easily had humans on Mars in the mid-80s. So we are actually living in a universe that is very boring by comparison to the one I expected as a kid to be in. What I've actually ended up spending my career doing is sort of pretending to be in human exploration of Mars. I mean, literally, you know, doing things like the Devon Island activity, and actually recently I've been working at the Mars Desert Research Station, which turns out to be a fabulous analog of Mars, much better analog than I think anyone realized when the site was selected, and a very interesting and useful analog for the MSL mission. So, you know, going out and doing research out of the Mars Desert Research Station is, in a very real way, it is my missions to Mars, you know.